Welcome to Section 1. Introduction. Elevating Software Design with QMOOD. Object-oriented programming has revolutionized software development, introducing powerful concepts like encapsulation, inheritance, and polymorphism. These concepts promised improved code organization, reusability, and maintainability. However, realizing these benefits depends heavily on the quality of the object-oriented design itself. This is where QMOOD comes in. QMOOD stands for Quality Model for Object-Oriented Design. It is a framework for evaluating the quality of object-oriented designs. Developed in the late 90s, QMOOD emerged from the need to establish a standardized approach to assess and improve the design of object-oriented software systems. Before QMOOD, there was no widely accepted standard for measuring the quality of object-oriented designs. QMOOD addresses this need by providing a set of 6 quality characteristics, often referred to as quality attributes or factors. These characteristics are understandability, maintainability, flexibility, reusability, extensibility, and effectiveness. Each of these characteristics plays a crucial role in determining the overall quality of a software design. By evaluating a design against these 6 characteristics, developers can identify potential weaknesses and areas for improvement. This proactive approach to quality assurance helps ensure that software systems are not only functional, but also robust, adaptable, and easy to maintain. In the following sections, we will delve deeper into each of these characteristics, exploring their significance and how they contribute to building better software. Now let's dive into Section 2. Understandability, the cornerstone of quality. Understandability in software design refers to the ease with which a developer can comprehend the structure, functionality, and interactions within a system. A highly understandable design is characterized by clear, concise, and well-documented code that reflects the problem domain it aims to solve. This clarity is essential for effective collaboration among development teams, efficient maintenance, and successful evolution of the software over time. Several factors contribute to the understandability of an object-oriented design. One key factor is the proper use of abstraction. Abstraction involves representing complex systems in a simplified manner, hiding unnecessary details, and focusing on the essential elements. Well-defined classes and interfaces, with clear responsibilities and minimal dependencies, significantly enhance the understandability of a design. Another critical aspect is the use of meaningful names for classes, methods, and variables. Descriptive names that accurately reflect the purpose and functionality of the code elements can greatly improve readability and reduce the cognitive load on developers trying to understand the code base. Furthermore, clear and concise documentation plays a vital role in enhancing understandability. While clean code should be self-explanatory to a large extent, well-written comments and documentation provide valuable context, explain design decisions, and highlight potential pitfalls. By prioritizing understandability, developers lay the foundation for a maintainable, extensible, and ultimately successful software system. Moving on to Section 3. Maintainability, reducing the cost of change. Maintainability is a crucial aspect of software quality that directly impacts the long-term cost and sustainability of a software system. It refers to the ease with which a software system can be modified, enhanced, and corrected to address defects or adapt to changing requirements. A highly maintainable system is one that minimizes the effort and risk associated with making changes, ensuring that the software remains adaptable and valuable throughout its lifecycle. One of the key factors contributing to maintainability is modularity. A modular design breaks down a complex system into smaller, independent units of code, each responsible for a specific functionality. This separation of concerns makes it easier to understand, modify, or debug individual components without affecting the rest of the system. Another important aspect is loose coupling between modules. Loose coupling means that modules have minimal dependencies on each other, reducing the likelihood that changes in one part of the system will cascade into other areas. This independence allows developers to modify or replace components with minimal impact on the overall functionality of the system. Effective error handling and logging also contribute significantly to maintainability. By anticipating potential errors and implementing robust error handling mechanisms, developers can prevent unexpected system crashes and facilitate quicker debugging. Detailed logging provides valuable insights into the system's behavior, aiding in identifying the root cause of issues and streamlining the maintenance process. By prioritizing maintainability, developers can ensure that software systems remain adaptable, reliable, and cost-effective to maintain over time. Finally, let's explore Section 4, Flexibility, adapting to evolving needs. In today's rapidly changing technological landscape, software systems must be designed with flexibility in mind. Flexibility, in the context of software design, refers to the ability of a system to adapt to new requirements, integrate with emerging technologies, and accommodate evolving user needs without requiring extensive rewrites or redesigns. A flexible design anticipates change and provides mechanisms to incorporate modifications with minimal disruption to the existing system. One of the key principles that contribute to flexibility is the Open-Closed Principle, OCP. OCP states that software entities, classes, modules, functions should be open for extension but closed for modification. This means that new functionality should be added by extending existing code rather than altering it directly. This approach minimizes the risk of introducing bugs into existing code and allows for easier integration of new features. Another important aspect of flexibility is the use of design patterns. Design patterns provide proven solutions to common software design problems, promoting code reusability and flexibility. By leveraging established patterns, developers can create systems that are inherently more adaptable to change. Furthermore, a flexible design often incorporates configuration options and parameters that allow for customization and fine-tuning of the system's behavior without requiring code changes. This adaptability is crucial for responding to evolving user needs, market demands, and technological advancements.